In this video, we'll do an example of trigonometric substitution where we'll have an integral containing one of the form a squared minus x squared. For this one, you're to evaluate the integral dx over the quantity 16 minus x squared raised to the 3 halves. So in this case, our a would be 4 because the 16 minus x squared is the same thing as 4 squared minus x squared. So our a is 4 in this case. So what we would do is we're going to let x equals to a times sine of theta, which in this case will be 4 sine of theta. So that gives you then that dx is equal to 4 cosine of theta d theta. Now doing our substitution, so we have that this integral of dx over 16 minus x squared to the 3 halves. Doing our substitution, we get this would be the integral. Instead of dx, we have the 4 cosine of theta d theta all over, and this would be the quantity 16. Now instead of minus x squared, that'll be minus this quantity 4 sine of theta squared, so that'll be 4 squared, which would be 16, and then sine of theta squared, so sine squared of theta. All of that raised to the 3 halves. Now both of those terms in the denominator have a 16, so what we could do is we could factor out that 16 and pull it outside the parentheses. But now remember, when you do that, let's see, so we have the integral of that 4 cosine of theta d theta still, all over. Now when we pull out the 16, it won't just be 16 on the outside. Remember, all of that was being raised to the 3 halves, so this will be 16 to the 3 halves times the quantity 1 minus sine squared of theta to the 3 halves. So that'll be the integral of 4 cosine of theta d theta. 16 to the 3 halves, that would equal to 64. And then 1 minus sine squared of theta, remember that's equal to cosine squared of theta. And then that's raised to the 3 halves. So this will be the integral of 4 cosine of theta d theta all over 64. Now cosine squared of theta raised to the 3 halves, that'll be cosine cubed of theta. Now simplifying what's inside here, this will be the integral of, let's see, so the 4's would cancel, so we'd have still 16 in the denominator. And then one of the cosines cancel, so this would be d theta over 16 cosine squared of theta, which would be the same thing as the integral of 1 over 16 secant squared of theta d theta, which integrating that'll give you 1 over 16 tangent of theta plus c. Now remember, we're not done yet, because remember the original integral had x's, not thetas. And when you're doing the trigonometric substitution, after you integrate it, then what you got to do is you got to do your back substitution. And then to do the back substitution, you often got to create the triangle to see what is this tangent of theta in terms of x. Or remember, we have that x equals to 4 sine of theta, which meant that sine of theta equals to x over 4. So if we have this right triangle where we have the angle theta, where sine of theta is equal to x over 4, remember that would be what the opposite over hypotenuse, so the side opposite of theta would be x, the hypotenuse would be 4. So using the Pythagorean theorem, what you would end up getting for the side adjacent, that would equal to the 4 squared minus x squared, so this will be the square root of 16 minus x squared. So this tells us that tangent of theta, which would equal to what? Opposite over adjacent, that would be x over the square root of 16 minus x squared. So therefore, substituting that in for tangent of theta, we get, rewriting the integral, that the integral of this dx over the 16 minus x squared to the 3 halves, that all equal to 1 over 16 times tangent of theta, so it'll be x over the square root of 16 minus x squared plus c, which, well, you could simplify just by multiplying those together. So this would be multiply the numerator, so that would just be x, multiply the denominator, so it would be x over 16 square root of 16 minus x squared plus c.